Good evening. This is the first of 3 lecture presentations for the electrochemistry unit. This is our last unit for AP Chemistry before the exam, so that is an exciting fact. During this unit, we will be explaining the relationship between the physical components of an electrochemical cell and the overall operation principles of the cell. We will explain whether an electrochemical cell is thermodynamically favored based on its standard cell potential and the constituent half reactions within the cell. This first video is going to focus on the spontaneous processes dealing with the creation of a voltaic or a galvanic cell. Let's quickly review a few terms for our electrochemical cells. The first thing that we're going to look at is the reaction between zinc and hydrogen ions coming from an acid, forming zinc 2+ and H2 gas. So the first thing that we want to look at is the definition of an oxidation. Please remember that the oxidation is the losing of electrons. So we have a couple different ways that you can remember it. We have the Ole with the oxidation is losing electrons. Love that one because I love Mexican food. You have the accent grave coming off of the E there as well for the Ole. So you have that. We also, when we're looking at this reaction in particular, we know that the zinc is going to be losing electrons. And so as a result of that, it will be the oxidized substance. We will call this the reducing agent. That is not something that is required on the AP exam any longer for you guys to know, but it is something that when you get to college it will be important. So you can just think of it as being like the opposite. Whatever substance is being oxidized is causing something else to be reduced, and so as a result we call it the reducing agent. So in this particular reaction, because if you notice with the zinc, it is losing the electrons to go from the Zn as a neutral element, Zn as a solid, going to the Zn2+. It has lost 2 electrons, so therefore it would be oxidized and would be classified as the reducing agent. The one characteristic that you can look for with a oxidation process is that the oxidation number is going to increase or become more positive or less negative. When we look at the reduction, you can see in this particular instance that the reduction is going to be the substance that is gaining electrons. So when we're looking at this particular half reaction, or the overall reaction, the 2H plus is going to H2 as a gas, so I'm going from a +1 to a 0, so I'm getting more negative in the value, so therefore it is undergoing reduction, and you can have the oxidizing agent being the substance that is reduced, and you can see that the hydrogen ion again is undergoing the reduction process. So there's a couple other ways that you can do it. The traditional Leo the Lion says GER, where losing electrons is oxidation, gaining electrons is reduction. You have the Ole, at least for the oxidation, and then the last one that you can look at is oil rig. And with oil rig, oxidation is losing, reduction is gaining. And so if you just remember that this is all in terms of the electrons, it makes it pretty easy to remember which is which. Let's quickly review the assignment of oxidation numbers. In order to keep track of what electrons are lost and what electrons are gained, we assign these elements oxidation numbers. Anytime that you have an element that's by itself, it's going to have an oxidation number of 0. Any neutral compound that you have will have the sum of their oxidation numbers equaling 0. If it's an ionic compound, it'll just be the traditional charge from the periodic table that we would use. If it's covalent, then they have hypothetical charges, so you'd look at the charge on the second element, which we would consider the hypothetical anion, and that one should always be kind of a constant, and then we can figure out based on the compound what the charge for the hypothetical cation or the first element would be in that covalent compound. If you have a polyatomic ion, the sum of the oxidation numbers must equal the charge for the ion, and then you have a specific list of elements that have characteristic oxidation numbers. So for instance, hydrogen, when it's combined with a nonmetal, will always be a +1. When it's combined with a metal, it'll be a -1. Fluorine is always a -1 in all of its compounds, no matter what, since it's the most electronegative element. Oxygen, being the second most electronegative element, will have an oxidation number of -2 in most compounds, although it will have a -1 charge in your peroxides. And if it's combined with fluorine and with fluorine only, it'll have a +2 charge. Most of your halogens will be a -1 when they're combined with something else, but if it is combined with another halogen or oxygen, then it can have a positive charge that is associated with it. So you need to look at the compounds and just kind of work backwards to figure out what will give the compound a sum total of 0 for its charge. There was a video that I did back in the fall, which is methods for balancing redox reactions. If you need some review, I would go and watch that video. I'll put a tag on that video for the end of this video. So let's begin by looking at a couple of example problems where we're assigning oxidation numbers. We're going to assign oxidation numbers for the elements in the nitrite and chlorate ions, NO2- and ClO3- respectively. So the first thing that we want to do is set up a little data table. It's something you don't have to do if you remember what to do, but I always find that people get a little bit better idea of what's going on when I put it into a table form. So I'm going to start off just by placing the number of atoms and the oxidation number. And then on the bottom, I'm going to write the overall charge for the compound or the ion. So when I look at this, I have 1 atom of nitrogen. When we're assigning oxidation numbers, a little bit different than charges because it's a hypothetical. So we always put the sign in front and then we put the number behind it instead of like we do with charges, where the number comes first and then the sign. So again, we always know what the anion would be, or the second element in the compound. So for those 2 atoms of oxygen, I know that each one would be a -2. We have your, again, oxygen typically being -2 in most compounds. You have the fluorine, the peroxides, and technically you have superoxides where it can have a charge other than the -2. I'm going to assign the nitrogen as the +X because we don't know exactly what it's going to be. However, what we do know is that in this compound, or in this ion, the sum total should equal a -1. So when I'm setting this up, I have X plus a -4 equals -1. So I know that the nitrogen must be a +3. Always report your oxidation numbers on a per atom basis. So I have the -2 for oxygen, I had the +3 for the nitrogen. When we look at the next example with the chlorate, we have Cl and we have O. Once again, I have 1 atom of chlorine, I have 3 atoms of oxygen. So I'm going to assign the chlorine as a +X again, and the oxygen as a -2. So I have 3 times -2, giving me a -6. And just like the nitrite ion, the chlorate ion must add up to equal -1. So in this case, my X must be a +5 for that to be the case. Now, just as a little point of aside for you, please understand that there are going to be compounds that have a fractional charge, and that is perfectly okay, or fractional oxidation number. So want to give you an example for something like that, where we have a fractional oxidation number. And an example for that would be propane, which is C3H8. Remember, with our hydrogens, if it's bonded to a non-metal, then it has a +1 charge. So when I set up my data table with the C's and the H's, I have 3 atoms of the carbon. I have 8 atoms of the hydrogen. Each one is a +1, and I'm going to put just a -X for the carbons. So I have a total of +8. Notice in this case, it is not an ion, so the sum of my oxidation numbers should equal 0. So now at this point, I have a total of -8 to equal the X value, However, I have 3 atoms that's being assigned to. So I can divide that by 3. So I have a fractional oxidation number of negative 8/3 to go along with the positive 1. That's okay. You might be going, wait, how is it possible to have a fraction of an electron being transferred? It's not. This is just a bookkeeping method. So just understand that within that structure for the propane, the 2 outside carbons are both a positive 3, and then the interior carbon is a positive 2. So if you think about the structure for propane, where I have all single bonds, you can see how each of the outside or terminal carbons are bonded to 3 other hydrogen atoms. So those would be a positive 3 and a positive, or negative 3, excuse me. Negative 3 and a negative 3. And then because this carbon here is bonded to 2 carbons and 2 hydrogens, it could be a -2. So the sum of my charges, -3, -2, -3, gives me a total of -8, and it's distributed over 3 different atoms. Like I mentioned at the beginning, we are going to focus on spontaneous processes. So when we look at the reactants for this particular reaction, we have zinc metal reacting with the copper 2 ion. You can tell the copper 2 ion, if you recall, from that characteristic blue color for the solution. So when we stick in the zinc electrode into the copper solution, what we find is that we have a direct transfer of electrons between the zinc and the copper ions in the solution. And so as a result, all of the energy that is changing places between the reactants and the products is not able to be harnessed. So the whole point of electrochemistry is finding a way where we can harness that energy and turn that into useful energy instead. So you can see here, when we look at the products, you can notice here as more and more of the copper is plating onto the solution, gaining the electrons, you can notice a characteristic change in the color of the solution. It's going from that very distinct blue to more of a dull bluish gray color, and eventually it would go to a clear colored solution. And you can see the zinc is very shiny outside of the beaker. On the inside of the beaker, you can see it's starting to turn a dark color, and that is the zinc that is being replaced by the copper atoms on the surface of the metal. And you can see in the right hand picture very large clumps of copper that have formed as the zinc is replacing the copper ions in the solution. So I also want to take a moment to review how to determine the balanced redox reactions from a half reaction method. So this method is going to divide the overall reaction into an oxidation and a reduction half reaction. The half reaction is balanced for mass and for charge. So again, mass in terms of the atoms, but we want to balance it in terms of charge for the flow of the electrons. One or both are multiplied by some integer to make the number of electrons gained equal the number that are lost. The half reactions are then recombined to give the balanced redox equation. And when we talk about these types of reactions, there's a number of different things that we can look at. The separation of the half reactions actually does a really good job of reflecting the actual cell compartments that we would have in electrochemical cells. The half reactions are easier to balance, especially if they involve an acid or a base. And usually it's not necessary to assign oxidation numbers to those species that are not undergoing a change. So with this half reaction method, we have titrations that we can perform, which would be called a redox titration. When we do that, we have one of the ions that's undergoing the oxidation or the reduction process change colors. So it's not necessary to have an indicator like we would for an acid-base type of titration, but in this case we can see the change in color as one of the substances undergoes some type of transition from one oxidation number to another. So you can see in this particular instance I have a very deep blue, purple color inside of the burette here, which would be the MnO4 minus ion. And as it reacts with something, in this case the oxalate ion, it loses that purple color immediately and goes to more of a clear color. At some point, when we have completely consumed all of the C2O4 2 minus, the MnO4 changes to Mn2 plus, and that has a pink color for the solution, or faint pink color, and so we can tell that the reaction is done when that faint pink purplish color stays intact in the solution. So I wanted to go through and balance a redox problem for you. This is being done in an acidic environment. So again, I did that whole video covering this stuff, so if you need to go back and review, please do so. But give us good practice for assigning oxidation numbers for each of our different ions. Now, as we're going through this, again, I'm not going to ask you guys to write out the chart every time, but just at the beginning, I wanted you guys to have that to figure it out. But in this case, I know that the oxygen is going to be a -2. 4 times a -2 gives me -8. I have a -1 charge overall, so I know the manganese has to be a +7. When I look at my oxalate, I have the 2 minus ion. 4 times the 2 minus would give me -8. It needs the -2 overall, so I'd have a +3 for the oxidation number of the carbon. And obviously the Mn2 plus, that would be a +2 charge. And now for the carbon dioxide, the sum of my oxidation numbers has to equal 0. So I have a -2 for the oxygen. 2 times -2 is -4. So I know the carbon would have to be a +4. So the next thing that we have to do in this process is identify what substance is undergoing the oxidation and what is undergoing the reduction. So the oxidation, again, getting more positive or less negative. You can see that I have the C2O4 2 minus ion, that oxalate ion, going to the CO2. Now remember, when we're balancing these things in the solutions, we need to look at the number of atoms of the non-hydrogen or oxygen atoms first. So if you notice, I have 2 of the carbons on the reactant side, only 1 on the product side. So I'm going to begin by placing a 2 out in front. You'll notice that now gives me 4 total oxygens, which matches what's found on the reactant side. So this is one of those rare instances where we don't have to add any water, but most of the time, to balance out your oxygens, we would add waters, and then we would add hydrogen ions to the other side to balance out the hydrogens from the water. So in this case, I can say that I have the 2 electrons. Again, it's just easy to do kind of a little charge check. Notice I have one ion of the oxalate ion, so that would be a -2 overall. And then I have 2 times 0 because carbon dioxide is a neutral compound. And then I have 2 electrons, so that would be a -2, so that gives me a total of -2. So we're all set on that first example with a balanced half reaction, and now I can move on to my reduction, and I have the MnO4 minus, and I'm going to draw some space here before I get to the Mn2 plus. So you can remember your oxidation, the electrons are always going to be a product, and then for the reduction, they're always going to be a reactant. So if you just remember the R's go together, reduction, reactant, for the electrons, you should be all set. So the first step I want to look at, I've got 1 manganese and 1 manganese, so my non-oxygen or hydrogen atoms are balanced. So I can now go and balance out my oxygens. Since I have 4 atoms of oxygen as a reactant and 0 as a product, I'm going to add 4 waters. I now have a total of 8 hydrogens, so I'm going to add 8 H+, and now I have everything else balanced except for the electrons. So there's a couple different ways you can do it. The easiest way, especially if you have coefficients of 1 for your substances, is to just look at the top. I have a 2+, and a 7+ for the oxidation numbers. So the difference between those, just thinking about a number line, that's going to be 5. So again, to go from +7 down to +2, I'd have to add in 5 electrons. So I now have my electrons balanced, so the last thing that I have to do is multiply my half reactions to make the electrons be the same for each half reaction. So since I have 5 and 2, I'm going to multiply the top reaction by 5, and I'm going to multiply the bottom reaction by 2. You can cancel any like terms on opposite sides of the equation. If they're on the same side, you can add them together. So I'd have now 5 for the C2H4, C2O4 2-. I would have 10 for my number of CO2s, and I'd have 10 for my number of electrons. I would have 2 for my MnO4. I would have now 16 for my H pluses, 10 for my electrons, 2 for my Mn2 pluses, and now 8 for my waters. You'll notice the only thing that is a like term on opposite sides will be the number of electrons. So I can now add everything together, and I would have the 5 C2O4 2- plus 2 MnO4- plus 16 H plus forms 2 Mn2 plus 10 CO2s and 8 H2Os. Now, one thing that I would like you guys to start doing, which will get you in good habits for our next lecture video when we start looking at calculating cell potentials from delta G values, just write off here an N, which is relating to your number of moles of electrons that are transferred. So since I had 10 electrons total, I'd have my N equaling 10. So it's just kind of a good habit for the way how a lot of these problems will set up in the free response section for the AP exam. So the last thing that I'm going to do is just do that quick little charge check to make sure that we have everything balanced. So I have 5 times A-2 plus 2 times A-1 plus 16 times a +1. So for my reactants, -10 plus -2, that's -12, plus 16, that would give me a total of +4. And now on my product side, I have 2 times a +2 plus 10 times 0 plus 8 times 0, because both of those are neutral compounds. Sum of their oxidation numbers is 0. So 2 times a +2 gives me +4 as well. You have a 98% chance that when you do this little charge check, if everything balances out for your charges, you've balanced your half reactions correctly. Just watch out for one thing though. There are some types of reactions, again, when we have the same substance undergoing the oxidation and the reduction process, where you can have whole number multiples for the entire reaction, so you'd have to typically reduce it down by a factor of 2 across the board. So that's that disproportionation reaction where one substance is undergoing both the oxidation and the reduction. So I just want to do a quick little rundown on the different types of electrochemical cells that we can have. The first one is what we call a voltaic cell, and in a voltaic cell, energy is released from the spontaneous redox reaction. So this one is also something that you'll see termed as a galvanic cell, and that just basically means that it will happen naturally. Again, thermodynamically favorable process occurring, so we don't have to do anything to help it along the way. You'll see here we have the 2 compartments separated from each other. So like we said a minute ago, you have the ability to have the different half reactions occurring in each of those chambers, and makes it a little bit easier to visualize what's taking place. When we look at the system here, It is providing enough energy to do work on the surroundings. So as the electrons transfer through the wire, there's some type of object there that's going to harness that flow of electricity, the flow of electrons, and it's going to be able to do work on the surroundings. The oxidation half reaction for this particular chemical system, we have the X going to the X plus an electron. So you can see again, the oxidation half reaction has the electron forming as a product. So as the electrons travel through the wire, they eventually come over to the cathode where they gain the electron. So I have the Y plus the electron going to the neutral atom Y or molecule Y that is present. And because it is a spontaneous process, we know that the overall reaction, when we combine the two cells, I'd have the X plus the Y plus forms X plus Y, but in that the delta G would be a negative value, less than 0, so we know that it would be thermodynamically favorable. When we look at the electrolytic cells, in this type of situation, the energy has to be absorbed to drive a non-spontaneous reaction in the opposite direction that it wants to go. So in this case, we have to supply power. So you think about like a lot of the types of electronic devices that we have nowadays, where instead of running off a direct current where the electrons are always flowing in one direction, they can be charged. And by charging those electrons, that's actually an electrolytic cell. So we're actually pumping the electrons back into the system, trying to force it to go in that non-favorable direction. So you can think about your voltaic cells, especially when you're talking about the concept of those DC currents. When you are paying your power bill as a future adult, you will essentially be just renting electrons from the power company. When we look at the electrolytic cell, because again we have a power supply, the surroundings will be doing work on the system. The oxidation half reaction, I would now have A minus going to A plus an electron, and I would have the reduction half reaction B plus an electron forming B. Now, when this occurs, the process still goes with the electrons flowing from the anode to the cathode. So that's something, no matter what type of cell, if you just remember the little acronym FAT-CAT, that'll help you out. So the electrons will flow from the anode to the cathode. Doesn't matter, you can see in both pictures, I have the anode here, the direction of the electron flow going to the cathode, still the same thing here. The only thing that's different is a lot of times we are pushing the electrons into the cathode to begin with, and as that process occurs, the imbalance is occurring within the cell. One other really big point to hopefully have you guys recognize here is that when we're talking about the voltaic cell, notice how they are in two completely separate compartments, whereas if you notice with the electrolytic cell, there's only one compartment. So that's a big, easy visualization for you guys on the AP exam to determine what type of process you have. If it's voltaic, it's going to be in two different compartments. So the last thing, just to wrap up your electrolytic cell, is again, it is for that overall reaction. A minus plus B plus forms A plus B, but notice in this case that the delta G for the overall reaction will now be larger than 0, or a positive number, which would represent the fact that it is a non-spontaneous or non-thermodynamically favorable process overall. I want to show you a couple different ways that we can represent the galvanic cell. Again, when we're looking at this particular diagram, notice that we have two separate compartments. We have something that we call either a salt bridge or a porous disk that go in between. This is kind of a gelatinous material that prevents the solutions from mixing together, but it allows the flow of certain ions to allow the charge to maintain its balance within the two different compartments. So you can see with this, we have a set of alligator clamps that are hooked up, and to each of the different pieces of metal, we call those electrodes. And we have the reducing agent, again, the substance being oxidized. And we have the oxidizing agent, which would be the substance that is being reduced. And just a way that you can kind of remember what the different compartments are, just think about a couple of different animals. So we have an-ox, where we know that the anode is oxidation. And we have red cat, reduction is at the cathode. So you have a couple different ways that you can remember what we have for the different cells, and then from there you just know that the electrons are being lost, so you always have that flow going from the anode to the cathode. One other thing that I just want to stress to you guys, kind of like I did when we were doing the organic chemistry back at the very beginning of the year, the direction is not always going to be from left to right. Just think about it from a situation of where your perspective is, what side of the beaker you're located on. The direction could very well be going from right to left instead of from left to right if you were behind the computer screen in this instance. So just be careful, because a lot of times they'll try to mess with you and put the anode on the right side and the cathode on the left. So just something to kind of watch out for as you start to look at problems. So here's another typical look for a voltaic or galvanic cell. This time we're using a salt bridge. And if you've ever wondered why we have those definitions for cations and anions, it's because of the ions that are in the salt bridge and the direction that they move within these voltaic cells. The oxidation again is occurring at the anode. The reduction occurs at the cathode, and then that little side compartment piece linking the two together, that's what we call the salt bridge. You saw the porous disc in the other example, but this allows the ions to flow without extensive mixing of these solutions. So that salt bridge, you're going to have a strong electrolyte that's going to be held in some type of gelatinous material. It allows for the passage of the smaller ions, but it hinders the flow of most of the ions that are in the solution that are more massive. So you always want to choose some type of ion or ionic compound for the salt bridge that is going to have no reaction with anything. We want it to be spectator ions, so just be careful in your choice. Some of the obvious ones that would be great ideas to use would be your alkali metal nitrate type of compounds. So if I have an alkali metal nitrate, again, all alkali metals are soluble, all nitrates are soluble, therefore it won't react with anything. What we don't want is to use something like sodium chloride. With quite a few of the reactions, sodium chloride would be fine for a choice, but if any of those compartments contained one of those ions, lead, mercury, silver, or the copper 1 ion, where the chloride ion would produce a precipitate, that would drop the concentration of the cell compartment down and would render that electrochemical cell dead within just a few seconds. One other characteristic piece that you will see when we are dealing with these galvanic cells is that as the process occurs, we have the zinc and the copper reacting together, as we saw, and now we have them in separate compartments from each other, so you're not going to see the plating of the copper on the zinc. you're actually going to find that the copper is going to plate on itself. So for the half reaction that's occurring at the anode, I would have the Zn as a solid going to Zn2 plus and 2 electrons. I would have at the cathode the copper 2 ions in the solution plating onto the copper metal as more electrons come in and forming neutral copper atoms. What I do want you to notice though is the direction of flow on the salt bridge. This is something that you'll have to label all the time. And so as I was saying, if you ever wondered why we call something an anion or a cation, it's due to the motion of those ions in the salt bridge towards either the anode or the cathode. We want to have a balance in the solution. So if you notice with my half reaction for the oxidation, I have the Zn coming into the solution and forming Zn2 plus. So I'm getting a more positive cell compartment on the left. And so to balance out that charge, you'll notice that I have SO42 minus ions migrating into the anode. So the anion from our ionic compound migrates towards the anode. When I look at the reduction half reaction, I've got the copper 2 plus ions adding 2 electrons and forming copper as a solid. So you will notice in that situation now the sodium, to balance out the loss of charge in the solution, the sodium is migrating towards the cathode. That's why it's called the cation. The last thing that I want you guys to notice here is the mass for the electrodes. When we're dealing with the anode, because we're losing the metal atoms and having them go into the solution as the cations, the mass of the anode is going to get smaller. And you can see in the picture here, as we add more electrons in, we start to get the plating of those copper ions onto that copper electrode, and I have a larger mass that forms. So you can use that as, some type of evidence. A lot of times they're not going to tell you what's the cathode and what's the anode. They're going to give you observational pieces to have you determine what's taking place within the compartments. So you can see here, as we look at the overall reaction, I have the Zn plus the copper 2 plus ion forming the Zn2 plus and the copper as a solid. If we look at an actual picture of what the electrodes would look like in the solution, you can see that the zinc that's here on the left side has gotten much, much thinner in the solution, and the copper has gotten larger. So again, in terms of mass characteristic observations, we know that the anode will lose mass and the cathode will gain mass. So just a couple of ways that you can tell what is taking place within the electrochemical cell. The last thing that I'm just going to mention here is a lot of times they'll ask you to make diagrams for the reactions that are taking place. Like I said, if it's a galvanic cell or that voltaic cell, then you're going to typically have 2 compartments. You'd want to label the electrode, you'd want to label the solution, you would want to label the salt bridge and show the migration of the ions, which direction they're moving, and then just put a random voltmeter up on top where you can measure the electromotive force, which we'll talk about in a little bit, or the voltage through the chemical system. So this would be the diagram that you would want to set up. There are some instances where if I don't have a solid as part of the reaction, we can use something that we call an inert electrode, such as graphite or platinum, where it's a non-reactive substance that will allow the electrons to flow through them easily. So they're good conductors, but they're not going to take part in the reaction overall. So if you have solutions such as like the MnO4 minus going to the Mn2 plus, you would use an inert electrode in there. They would still have mass being gained on one side and for the inert electrode as the one of the substances could come out of solution into a solid, but typically you would have those in solution, so you'd see no change in mass for your inert electrodes. We have a labeling system that we can use to denote the voltaic cells. We would start off by, on the left side, putting the components of the anode compartment, the oxidation half reaction, and then on the right side we would have the cathode compartment, or the reduction half cell. So in this we separate the barrier, kind of like the salt bridge, as showing that as the double line. A little hard to see there, that's a double line, but it is. You can separate the different phases by using a single line, so looking at like what the electrode is and what the solution is for each side. So we put the phase of the lower oxidation state on the outside. Typically that's going to be your electrode when we're talking about the anode compartment. And then the phase of the higher oxidation state, that's going to be your solution. And then for the cathodic reaction or compartment, you would now have the phase of the higher oxidation state. So again, I'd have the solution and then the lower oxidation state, which would typically be your electrode. So again, states of matter would be important here. Just as a heads up for you, if your electrode again is an inert electrode and you have the two substances undergoing that process that are both in solution, you would separate them by a comma in the solution part of the compartment. So I have the electrode, a single line, the solution, a double line, and again that represents the salt bridge. And then I have the solution and then the electrode once more. So again, these represent the phase boundaries between the different half cells, which again is basically our salt bridge. So if we look at an example here for that reaction that we just did, I had the zinc going to the zinc 2+ ion. So I had the zinc electrode, the lower the oxidation numbers with a 0 oxidation number, going to a +2. I have the double lines to show us the salt bridge, or that boundary between the different half cells. And then I come over to my cathode compartment and I had the Cu2+ that's in the solution going to the Cu as a solid electrode. So I have the half reaction, Zn as a solid goes to Zn2+ plus 2 electrons, copper 2+ plus the 2 electrons forms the copper as the solid. You don't have to list out how many electrons are present in the process, just what is actually taking place within the compartments. So like I said, as an example, if I had a substance that was an inert electrode, I could have something like this, where I have the graphite, there's my inert electrode, I have the I-, and it could go to the I2 as a solid, and then I have the H+, the MnO4-, and the Mn2+, and then I have the graphite. So again, I'm listing what my reactant substance is first, then I'm listing my product substance. Notice again I have another separation of the phase change there. So I have a second single line, and then I have the graphite electrode on the other side as well. So again, we have the inert electrode as the graphite in that solution. Now, as we move on, this is just showing us a list of the orders of reactivity for the different metals in solution. We equate this to our activity series that we learned about for your single replacement reactions. So as you go higher up the list, you have the more reactive metals, and that means that they're going to undergo that oxidation process more easily. So it works in the exact opposite direction as we go down the chart. Then that tells me with the ease of the reduction that will take place. So we can look at this to kind of give us a general sense based on their positions, which elements would react with others, to provide that thermodynamically favorable process where, again, the delta G is less than 0. So we look at an example for this. We can look at the standard reduction potentials for SN2+ and Ni2+. And when we do this, we want to see which one has the greater, more positive standard reduction potential. Now, as we go through these two, the reductions, again, being very specific, I have the Ni2+ adding 2 electrons, forming the Ni as a solid, and I compare that to the Sn2+ plus 2 electrons, forming the Sn as a solid. Now, when we look at this, the nickel and the tin were directly above and below each other. So the further up we have, that would have the element with the greater oxidation potential. So the one that has the more positive standard reduction potential is going to be the one that is below. So in this case, the substance that would be more readily reduced would be the tin. Because the nickel is above it, that means that it has the tendency to undergo oxidation more so than the tin would. So when we combine these normal elements along with some of our different polyatomic ions that could undergo the reactions, or some of our nonmetals, we get a list of standard reduction potentials in water for a number of different half reactions that take place. The more positive the value is, the more likely that substance is to undergo reduction. The more negative it is, the more likely it is to undergo the oxidation process. So you can see here, fluorine is our most heavily reduced substance. It can go from the F2, adding 2 electrons, to the 2F minus. And lithium is our most likely to undergo oxidation, with taking the Li as a solid, going to Li plus, and the electron that would be produced. Just remember, opposite processes. If I undergo oxidation, that's losing the electrons. If I flip the direction of the reaction, then that would make it a reduction, and we would change the sign. So again, the most positive substance on the reduction potential would undergo the reduction for a reaction. The most negative for the reduction potential would mean flipping the sign. I'd have the most positive for the oxidation. So that's how we can compare the different values for these different half reactions using these standard reduction potentials. All right, so let's take a moment to do a little concept check here, and we're going to order the following from strongest to weakest oxidizing agent and justify. Of those that you cannot order, explain why. So again, because we're talking about an oxidizing agent, that means that we're looking for substances that undergo reduction. So as I start off this process here, there are a couple that we can look at. Number one, the Na as a positive could be reduced, and if we looked at that half reaction, Na plus an electron going to Na as a solid, it was a negative 2.71 for the value. For the Cl2, that one had a positive 1.36, and that was the Cl2 going to add 2 electrons and forming 2 Cl minuses. So again, the stronger the reduction process is, the more positive the value will be. So the strongest we would have would be Cl2. The weakest that we would have would be the Na+. Now, of the other three, we can look at those substances, and for my two metals, again, think about what that reduction is doing. We're adding electrons into those substances. And so since I have two metals that are both neutrally charged, these would be forming anions in the process, and that's not something that typically happens. So there are no values for these two substances on the chart. And then finally, the F minus, again, if you think about that being the period 2 element, remember we cannot have expanded octets, so adding a second electron into a fluorine ion would cause the electron to have to go into that third energy level, and that would be a very tall task to perform. So the three that are circled, those would be the unidentified. For our different orders, they would be impossible to tell because they have no values. But because I have the negative 271 and the positive 136, I know that the more positive is the more desirable for that particular process. And so as a result of that, the Cl2 would be the stronger oxidizing agent compared to the Na+. The values that we saw on the standard reduction potential table, those values are referenced to a standard hydrogen electrode, SHE. By definition, we have set the hydrogen electrode to have a reduction potential equal to 0 volts. So we'd have a half reaction, 2 H pluses plus 2 electrons, again aqueous for the solution and 1 molar for that standard concentration, forming H2 gas, which would be at 1 atmosphere of pressure. That hydrogen electrode would then be referenced as part of a half cell with some other substance, and we can see the change in the energies that are electricities based on the flow of electrons that would be present within those systems. Now we're going to learn how to calculate the cell voltage, or the potential difference for a reaction. By convention, all of our electrode potentials are written as reductions, so we're always looking at the two substances gaining electrons. However, we know that within any type of chemical reaction, the number of electrons that are lost, the oxidation, must equal the number of electrons that are gained. So when we're pairing the two half cells, you have to reverse one of those reduction half cells to produce an oxidation half cells. When that occurs, you're going to reverse the sign of the potential. Which one you choose, again, remember, the more positive the value is, the more likely or the greater tendency that substance is to undergo the reduction. So the more positive standard reduction potential, so I'm just going to call that SRP, the more positive that standard reduction potential is, the more likely it is to undergo the reduction. So I would take and keep the more positive value as the reduction half reaction, and then I would flip the less positive or the negative reduction potential and make that the oxidation. At that point, all you have to do once you flip them is add the two together to give you the total for E cell. Now, again, just like with delta G, when you see the E naught, that again is talking about standard state conditions. So when we talk about the standard conditions for the solutions, we're talking about having a 1 molar solution. If we're talking about having gases, it would be 1 atmosphere, and just like thermochemistry, temperature-wise, we'd have the 25 degrees Celsius. So when we do this, you can just simply see the E cell for the particular reaction would be equal to the E for the reduction plus the E for the oxidation. A lot of times you're going to see in your textbook them telling you to subtract the reduction and the oxidation for the standard reduction potentials, but it's just easier to flip the reaction and then add them together rather than trying to always subtract a negative. So just something for you guys to think about. makes it a little bit easier to calculate. When we're writing the spontaneous redox reaction, the left side, the reactants must contain the stronger oxidizing and reducing agents. So just kind of think about it like we did with our acid and bases for the Bronsted-Lowry definitions. Again, we can look at the parent on the left side and the new substances that are formed on the right. We can typically have the acid and base being stronger than the conjugates, not all the time, but it can. And so with these, we always want to think about the substance that is a stronger oxidizing agent and a stronger reducing agent being on the reactant side, and then the weaker components on the right side. So you can see here in this that as far as a reducing agent, the zinc is a stronger reducing agent than the copper as a solid is. You know this based on like our single replacement reactions that we did where we'd have no reaction take place. If I put the copper metal into the zinc solution, I would not have zinc plate onto the copper metal unless I added electricity to it, because the reverse direction would be non-spontaneous or non-thermodynamically favorable. So the copper would be the stronger reducer or oxidizing agent and compared to the zinc, so those would both be the weaker on the other side. All right, so let's take a qualitative look at what's taking place inside a voltaic cell here really quickly. So I have two half reactions that are occurring in a voltaic cell. I have nickel as a solid going to nickel 2 plus 2 electrons. The electrode inside would be the nickel, again the solid, and then I have a second half reaction, Cu2 plus 2 electrons forms Cu as a solid, and the electrode would be copper. So I know, again, looking at my two half reactions, since they're both not listed out as standard reductions, I don't have to go to the table and look and see which one has the more positive standard reduction potential value. I can just look at the direction of the electron flow. So in this first half reaction, because the electrons are being produced, I know that that would represent the oxidation. And I know since the electrons are reactants for the copper, that this would then be the reduction reaction. Now, if you think back to the very beginning of the presentation here, when we're talking about the different electrodes that are found inside of the compartments, please remember that the cathode is going to be gaining mass because we're plating extra ions into the solution. And because we are plating those extra ions and taking them out of the solution, that means that my cell compartment is getting a more negative charge to it, or less positive. So in that case, I'd have to have the cation flowing towards the cathode. So when I look at my choices, focusing on the copper electrode and the copper 2 plus solution, again, the electrode would be gaining mass because it's the cathode, so I know I can automatically eliminate choices A and C. And then when I'm looking at my choices between B and D, I have the electrode is gaining mass and cations from the salt bridge are flowing into the half cell, or the electrode is gaining mass and anions are flowing from the salt bridge into the half cell. So again, to have that charge neutrality within the solutions, the balance of the charges, because I'm losing the positive charges, I know that the cations will flow into the cell compartment. So my answer would be B, and I can eliminate D from the choices. Okay, so let's take a look at a couple of example problems here. So the first one that we're going to do is we have a voltaic cell based on the reaction 2Eu plus Ni2 plus forms 2Eu plus Ni, generates an E cell value of 0.07 volts. Given the standard reduction potential of nickel, which is negative 0.28 for the Ni2 plus 2 electrons forming Ni as a solid, what is the standard reduction potential for this particular reaction? So again, it's asking me to solve for a standard reduction potential. So I know that the nickel is going to be undergoing the reduction. So it's got the negative 0.28. So again, to calculate the E cell, I'm taking the E for the reduction and I'm adding it to the E for the oxidation. So in this process, if I know that this is a negative 0.28, in order for the cell to have a positive 0.07, then my E cell for the oxidation must be, in this case, 0.35. But again, that's for the oxidation. So I know that my X for the oxidation part would be equal to a positive 0.35, but it's asking us for the standard reduction potential. So again, I need to flip the sign. So my correct answer would be A for this particular reaction, because notice again, it wants the electron as a reactant, so it wants the reduction potential and not the oxidation potential. So I have negative 0.35 for the first. When I look at the second example that we have here, I have the standard cell potential is 1.46 volts for a voltaic cell based on the following half reaction. Use the table 20.1, calculate the E cell for the reduction for the IN3+ to the IN1+. So if we look at the table, the bromine plus the 2 electrons forming the 2 bromide ions has an E cell value equal to a positive 1.07. So now in this particular situation, because it's looking for the indium to be the reverse reaction, in this forward direction here where the indium is a oxidation reaction, I know that when I add these two half cells together, it has to equal a positive 1.46 volts. So in order for this to occur, I know that the E cell would have to be a positive 0.39 volts for the oxidation half reaction. But since it wants it for the reduction, going from IN3+ plus 2 electrons to the IN+, I know that I'd have to flip the sign, so my E cell for this would now be equal to a negative 0.39 volts. And that would be my final answer. The one thing that I just wanted to make mention to you guys here, because we are talking about the cell potentials for these individual half reactions, the coefficients for them do not matter. The voltage is going to be an intensive property where it's not depending on the amount of matter that's present. So as a result of that, whatever the standard potential is for that particular substance, that's just what it is. You don't have to multiply it like we did for Hess's law. You don't multiply the half reaction's cell potential to get the overall balanced reaction. All right, so we're going to do one last example. Sorry, I know this one went way longer than I had wanted, but we're going to use one last example here to do a traditional problem where instead of having the standard electron potential, we're going to calculate what the voltage is for the cell. So if we go back and we look at the data from those from that data table for the particular half reactions, we can look at, we have the 2Ag plus, actually we don't need the 2 on here, the Ag plus an electron forming Ag as a solid, and the electron potential is 0.80 volts for that reaction. We had the previous reaction where I had the Ni2 plus 2 electrons forming the Ni as a solid, and that E cell was a negative 0.28 volts. So again, we had to flip this reaction, and so when we did that, we multiplied by -1, which converted that into a positive 0.28 volts. So I could now just add those together, and I have 1.08 volts for my answer. So the correct choice in this case, we know that it is a voltaic cell, so therefore we can eliminate any choices that have a negative voltage, because that would infer that it is a thermodynamically unfavorable process. and so it has to be the positive value for that particular substance. All right, so now you guys pause the video real quick and try to answer the next question. So again, as we look at this, I have Al as a 3+ charge being added to 3 electrons to form the Al as a solid, and the E cell for this process is a negative 1.66 volts. And when I look at the I2 plus 2 electrons going to the 2I minus, the E cell for this particular reaction is a positive 0.54 volts. So again, to choose which one is my cathode, I'm going to take the one that has the more positive value. So I know that this is the reaction that I want for my reduction. And then for my oxidation, I know that I would have to flip this reaction. So when I would flip that reaction, I would take my E cell for the cathode and multiply it by -1. So that would now become a positive 1.66 volts. I can add that to the 0.54 volts, and that would give me a total voltage of, I believe, 2.20 volts overall. All right, so this concludes the first lecture video. Again, I apologize about it taking so long, but I wanted to get through all the Voltaic Cell components first. The next video will be covering non-standard conditions. We'll go through this one a little bit quicker, but we'll talk about non-standard conditions for the E cell and how that is affected or affecting the voltage for the overall reaction, and that's going to introduce us into the Nernst equation. So we'll take care of that in lecture video number 2, which I promise will be shorter, and then the last one will be covering electrolytic cells for the 3rd video. So have a wonderful evening. Please come to class with questions tomorrow and work on the practice problems that are on Teams. See you in class.